Hello, my name is Adrian Rodriguez Marek. I'm a professor of geotechnical engineering at Virginia Tech, and my specialty is earthquake engineering. So I teach here at Virginia Tech. I teach about earthquakes, and I teach about the impact that earthquakes have on the things that we build.
Hello, my name is Martin Chapman. I'm a professor at Virginia Tech.
Hello everyone, my name is Mohsen. I'm a PhD student in structural engineering at Virginia Tech.
Hi everyone, my name is Tyler Quick and I'm a PhD student here at Virginia Tech and I research geotechnical earthquake engineering.
Hi, I'm Kaylee Yost and I'm a PhD student in the geotechnical engineering program at Virginia Tech. One of the reasons that civil and earthquake engineering is so important is because we don't know when the next earthquake is going to strike. While we have a good idea of what locations in the country might experience earthquakes soon, we don't know when they'll happen and we don't necessarily know how big they'll be. That means for people that live in earthquake-prone regions, it's really important to be prepared for an earthquake to happen at any time. As civil engineers, we work on all different aspects of earthquake preparedness, from determining where and when an earthquake might happen, to making sure that our structures can withstand earthquakes. After earthquakes happen, we also go into the field and see how different structures behave during the earthquakes. This helps us get better information about how to build our structures in the future.
Natural disasters such as earthquakes cause landslides that claim the lives of people in many parts of the world, particularly near active tectonic regions. To minimize the impacts of this in our communities, earthquake engineers strive to develop community-based and practical solutions to understand the soil beneath our buildings and their complex interaction with fluids such as water and gas. Also, some earthquake engineers are interested in the response of buildings such as skyscrapers and their oscillation with earthquakes. Nowadays, earthquake engineers have developed an array of tools using computers, experiments, and construction site monitoring to look out for the earthquake shaking and act quickly to evacuate these buildings before collapse.
When designing an earthquake-proof building, it's important to think from the ground up. Geotechnical engineers think about how the seismic waves from an earthquake travel through the soil and rock beneath a potential building site. Different soils and rocks will behave differently, and whatever type of soil is beneath the site of your building will interact with the foundations of the building. Think about a building constructed on a loose beach sand versus a building constructed on a foundation on rock. Do you think they would behave the same way when the ground shook from an earthquake? Probably not. Once the geotechnical engineers determine how the soil and foundations of the building will behave, the structural engineers decide how the building needs to be designed. To help buildings withstand earthquakes, structural engineers must make sure that the building is stiff enough to reduce the damage, but flexible enough to move with the earthquake. They could implement cross bracing, which turns a weaker shape, like a rectangle, into a stronger shape, like a triangle. Sometimes they might implement a base isolation system, where the structure is actually allowed to move separately from its foundation.
And the concept behind earthquake-proof buildings is to have high ductility. So ductility is when a material can deform without failing. Let me give you an example. Imagine you have potato chips between your thumbs. If you just push it, it breaks, right? However, if you have a rubber band and you pull it, it doesn't break easily. And that's the kind of difference between materials that are ductile or not ductile. Now, going back to earthquake engineering, we want structures that are not like chips. We don't want them to break easily. And we try to find materials that have this high ductility and use them so when earthquake happens, and as you can imagine, when earthquake happens, everything is shaking, and that shaking moves to the building and the stuff that's inside the building. So everything is shaking and there's like a lot of displacement, and if our materials have high ductility, they won't break easily. And that's what structural engineers tend to do. Now, the second thing is the art of putting all these materials that have high ductility together in a way that the system works nice and is like connected well, and all the materials get a chance to be ductile. Because imagine you are making a Lego. All the pieces, they are, you know, tough and have good quality, right? But if you connect them in a wrong order and then somebody push it, it just falls off. And we don't want that in our buildings. So the first thing is like to find these good materials with high ductility. And the second part is like to connect them in a way that they can sustain an earthquake.
The most important part is to think about earthquakes even before we construct buildings. Are we planning to place our buildings on a fault line? What is the lifespan of our building? Engineers need to plan ahead and optimize the hazard versus cost using statistics to ensure we do not overcharge our clients. We require our buildings to be ductile and not to fracture in a brittle and explosive manner. Hence, we need sufficient amount of reinforcement while still allowing our buildings to show failure indicators, such as small cracks, which act as alarm bells to help us evacuate the buildings.
And this is an interesting question because intuitively we think, okay, if we can make a structure that is earthquake proof, should we do it for everywhere? And the answer lies into the fact that not all places, for example, in the US have like high earthquake probability. Like there are places like California where we expect earthquakes to happen. And there are places that we don't accept earthquakes sometimes at all. And now going back to designing for earthquakes, you can imagine finding those materials and connecting them. We are spending money on that, right? And money is one of the aspects of designing a building. So a structure that is designed for earthquake is more expensive than a structure that is not designed for earthquake because all those additional things that we need to do. And if you spend all that money to build that structure for a place that an earthquake never happens, then you are not spending your money very smartly, right? And nobody wants to do that.
Today, I want to talk about, do we need earthquake-proof buildings everywhere? So we talked, a little bit about how bad earthquakes are. You can see pictures here. We have apartment buildings tipping over and harbors falling into the sea. Over here, you have cars falling, sinking into the ground. So obviously, earthquakes are bad. If they are so bad, why don't we go ahead and design for earthquakes everywhere, for every building you build? Well, as an engineer, you have to consider a lot of different things when deciding whether to design for earthquakes. So this is what we call a earthquake hazard map or a seismic hazard map. And this tells us, where are the earthquakes the worst? Where are the biggest earthquakes going to happen? Where are they going to happen, all the time, most often? You can see Blacksburg over here, and the rest of the United States. The color tells you how bad the earthquakes are going to be, generally. So in an area where it's white, like up here, we really don't have earthquakes. So up north, we don't really design for earthquakes. We don't put improvements into buildings. We don't put a lot of money into design for those things. In Blacksburg, we have a little bit of earthquake risk, this kind of grayish, greenish color. So we have small earthquakes. And so depending on what buildings we're building, we might include some things for earthquakes. But if we were to live in a place like California or over here, we would definitely design for earthquakes because we're going to get really big earthquakes and get them a lot. And so again, as an engineer, you look at these maps, and when you're looking to build a building, you have to consider, is this an area where there's lots of earthquakes? And if so, we definitely design for earthquakes. What else? We also, have to look at what our buildings built on. So if you were to build your house on rock or on sand, or say loose sand, where would you choose to build? Hopefully you build on rock. It's obviously sturdier for your house. And during an earthquake, similar things happen that, this house on rocks can do a lot better generally than this house on sand, because the house on sand might sink into the ground or might tip over. And so we're going to have to put a lot more seismic design and money into making sure this house or this building or structure is okay during the earthquake. So to answer your question, do we need seismic design everywhere? Well, the answer is it depends. It can depend on cost. Again, if we don't have to design for earthquakes and improve our buildings, we're not going to, because that costs a lot of money. You know, where do big earthquakes happen? If we're in an area where there's no earthquakes, we're not going to design for earthquakes. If we're in an area like California, we'll definitely design for earthquakes. What's the building built on? If we have a strong foundation, we may not have to put as much design into, or as much improvement into our structure to resist earthquakes. And then, you know, there's other factors too. You know, how important is the structure? Different things like that. You know, is the earthquake hazard likely to change? All those kind of things. So this is why we need seismologists and engineers like you guys and like us to find solutions to these problems, to look at ways to improve the way we do things, and to make sure that we all stay safe.
It's a very good question. Seismologists are scientists, and what scientists like to do is ask difficult questions. How do things work? How does nature work? How can we understand natural processes? How can we understand earthquakes? Engineers like to solve problems, but very practical problems. How can I build a building so that it doesn't fall down when an earthquake comes by? How can I design a bridge so that if an earthquake happens, the bridge doesn't move? So we work together. We have to work together, because engineers, we need to understand, we need to be told how an earthquake will affect, how much shaking will it cause on the ground, so that engineers can come and design a building so that it can stand up to that level of shaking. So what seismologists do is they look deeply into how earthquakes happen, and they tell us how strong the earthquakes will be. And then as engineers, we say, okay, we like this problem. We are told how strong the earthquake will be. And from there, we'll find out how strong the bridge or the house or the building that we are putting up has to be so that it doesn't fall down to that shaking. Another way of seeing it is that seismologists, they look at the problem purely from a question of understanding nature. That's all they care. But they don't worry that much about the applications, because they know that that's the job that we engineers do. On the other hand, we have to focus on solving a very practical problem, and we don't have neither the time nor the knowledge to try to understand in depth how nature works. And that's how we work together. Seismologists, they study nature and they tell us what we should expect from nature. And engineers, we take that knowledge and we pre-build our buildings so that we can withstand the shaking from the earthquakes.
We as engineers and scientists, we work together. We also work with seismologists. Seismologists help engineers look deep within the earth to understand the geophysics and the underground materials. Engineers then convert the theory into numbers that can be practically used in design. Seismologists often provide the seismograms, which are then filtered to make sure there are no noise in the readings. Engineers can then make estimates of the readings reliably and make judgments.
Well, they work together very closely, actually. Mainly what they try to do is to identify places that have high earthquake hazards. And they also work together to design and build structures that are safe when earthquakes do happen. Seismologists mainly keep track of where earthquakes occur, how often they may occur, and how much the ground will shake when they do occur at different distances from the epicenters of the earthquakes. Engineers use this information to develop building code maps. With information on how to design buildings in different parts of the country. That's what the building code maps do. They give you, depending on where you live in the country, they give you design criteria for building structures. So it's a that's how the interaction works. It's the seismologists mainly deal with locating earthquakes and trying to understand how the ground will shake. They give that information to the engineering community, and then they develop the design maps and the building code maps for how to construct high-rise buildings and small buildings and bridges and things like that.